Anybody come up with an idea of at least how to attack that problem? What's the idea?
The volume first and then the full amount would be.
Find the area of the whole thing.
Area of what whole thing?
Surface area.
Surface area?
Isn't that what it
No,
area
volume.
of distribution?
All right, I haven't heard what I was hoping to hear yet.
Oh, I got it.
What?
You take, well, first of all, you have to set it so that the center of it is going to be the x-axis, and then you're pretty much rotating a circle around the x-axis. And so by integrating the area of the circle over the period by integrating it over a period of flow, then you're essentially doing the whole thing that we did with the rectangles, except with circles, over the whole course of the tank.
Okay, I think you're kind of on the right track here, because at least you're saying integrate, and I think some of your method is correct in that. I don't think it has to be as difficult as that, though.
I'm just confused.
No, you're on the right track. You're on the right track. Let's first of all agree upon how you'd find the volume of just the cylinder itself. So if someone gives you a cylinder, right, the volume of a cylinder is what? Excuse me. The volume is pi r squared times the height, where the height is this, right? And the radius r is that, right? That's the volume of a cylinder. Do you recognize pi r squared? What's pi r squared? The area of the circle. So isn't the volume of this three-dimensional solid just the area of the surface here, like a cross-section area, times how deep it is? It's like infinitely many circles stacked on each other. So all you do is you find that one area up here, and then you multiply times, find that area, and then multiply times the depth, which is this, right? All right, so on this picture here, we've got our cylinder, our gas tank full of blue gas. Not full, but it's got the blue gas in it, right? Like this. So if I just take a look at that blue part, right? Just the blue part, then it would look something like, I don't know, like that. It's just part of a cylinder, yes? Mm-hmm. And so if I could maybe figure out what the area of that is, would it make sense to you that if I found out that area, then all I'd have to do is multiply by its height, and I should know the volume of that? Yes? So all I need is the area of that front face, this piece right here. If I can find that area, I'm in business, yes? Okay, so why don't we try and do that? So why don't we look at the gas tank from the end, okay, and make it a two-dimensional picture instead of a three-dimensional picture. I'm going to orient the bottom of the gas tank at the x, y axis cross point, so at the origin, right? Got this gas tank's coming in like this, like that, right? It's going up, it's coming around to circle, right? My gas is in here, and that's hitting where here on the y-axis? At 2. Do you agree? At 2 is where that's hitting, right? And so the area that I'm interested in is just this, right? In here. Just what's that area? And that's what we did last class. We tried to find the area between two curves, didn't we? Now there's some symmetry here, isn't there? So I could, if I want, just find the area of that piece and then double it. You want to do that, or you want to do the whole thing? I don't really care. You want to do the half and double it? Okay. So if we're going to do this, if we're going to get this half area right here, there's a couple of things we're going to need to know. First, where do we start our integral at? 0. So our integral should start at 0. Where is it going to end? We don't know. We've got to find where those intersect, don't we? I said where those intersect. That means you have to know this curve, don't you? That means you have to know the equation of a circle and somehow write it as a function of x. So we have to go back now and think about what is the equation of a circle? X squared plus y squared is r squared. That's the equation of a circle that's centered at the origin. Is r centered at the origin? No. Where's the center of our circle? If I draw it like this, where's the center of ours? Right up here at 3, 0, right? That's our center? Because it had a radius of 3, didn't it? You still there? Yeah. So this is the formula if we're at the center. It's correct, but that's not the one we want. We want x minus h squared plus y minus k squared equals r squared. That make more sense? I mean, not make more sense. Does that ring a bell is what I meant to say? Yes? Okay. What's h, what's k? What's hk? Hk is supposed to be the center of the circle, right? So h for us is 0, k for us is 3. So this equation becomes x squared plus y minus 3 squared equals, for us, what's the radius? 3, so 9. Agreed? Now, if I'm going to do this like we did last class, and I'm going to do vertical rectangles like this, and do infinitely many of them between 0 and something here, then I need to be able to rewrite this black curve as a function of x, don't I? To do vertical rectangles, which means you have to be able to solve this for what variable? For y. So can we solve that for y? Let's try. Running out of room here. So if I'm trying to get this in terms of a function of x and solve for y, how about we move the x squared to the other side? Right? And then what? Square root on both sides? Now I'm supposed to do plus or minus, aren't I? Yes? All right, so which one am I going to do, the plus or the minus? Because it can't do both. Let's see. Let's take a look. I'm going to put this, or it could be this. Do you agree? Could be one of those. Which one is it? So what we have to remember is that this is a circle, right? It goes around. And so circles fail the vertical line test to begin with. They're not true functions of x. But when we do this and we get a plus or minus, one of them is the bottom of the circle, the other one is the top of the circle. So there's two halves. That's what this represents. Let me move the 3 to the other side. So we have either y equals root 9 minus x squared, plus 3, or we have y equals negative root 9 minus x squared plus 3, right? Or which one? So which one is it, and tell me why? Bottom one, why?
I think it's going to be the top one.
Top one, why?
Because the slope is going to be positive.
Slope?
Well, the slope is going to have to be positive in order to.
Yes.
I think it's going to be negative. Aren't we working with the bottom half of the circle?
Mm-hmm.
Because we're trying to find the area under that.
So you're thinking the bottom one because it's the bottom half?
Yes.
So use the negative. Well, how about this? Isn't the bottom half have to contain this point? So when I plug in x equals 0, I better get what? 0 for y? Okay, try it in here. If you plug in x equals 0 right there, you get 9. Root 9 is 3. 3 plus 3 is 6. Oh, wait, that's the top of the circle. You see that? You plug 0 in here, you get root 9, negative. That's going to be negative 3 plus 3, that's 0. So this bottom function is the one that's going to generate the bottom part of the circle. Is that fair for you? Okay, so this one's gone. All right. Any questions so far? So now, I'm going to go and try and get where they intersect each other. So I need to do where this blue curve hits the black curve. That means I need to set this function equal to what? 2, right? Y equals 2. So for the intersection, I need to set negative root 9 minus x squared plus 3 equal to 2. Which means I'm going to move the negative root to this side. I'm going to move the 2 to this side. So 1 equals root 9 minus x squared. You all still there? Square both sides. 1 equals 9 minus x squared. X squared equals 8. X equals plus or minus root 8. And I'll do the plus 1. Why am I not going to do the minus 1? It's on the other side, and I'm only going to work on this side, and I'm going to double my answer, right? So root 8, is that good? Okay. So I know where to integrate from, right? 0 to root 8. I just need to now figure out the top function minus the bottom function, right? That's what last class was about. F of x minus g of x, that gives us the area. So integral goes from 0 to root 8 of the top function minus the bottom function d, is it y? Which way is our rectangle? Vertical. Vertical means dx. Horizontal rectangle is dy. So I'm integrating with respect to x. The top function we said was what? The constant 2 function, right? That's the function. This line right here is y equals 2, isn't it? Flat line. So that's the top function. Minus the bottom function, which is, I erased it. I need a little more room. What's the bottom function? Negative root 9 minus x squared plus 3. If we can integrate that, that's the area of that front piece, right? But we're supposed to do what with it? Double it. So twice that will be the area, right? And then what should I do with that to get the volume? Multiply it by the depth of the tank deep that way, which was 12, right? So do y'all want to just stick with area for now and then get the volume later? This is the area, that A, that's what we're looking for. All right, let me try and clean that up a little bit. So the area equals 2 integral 0 to root 8. Because of the symmetry of the problem with that circle, we were looking only from 0 to 8 to get this area, but we said if we want the area of the whole thing, we were going to have to double our answer. So the 2 was just to pick up the other side. What number goes in there? Like I can distribute this, right? So 2 take away 3, negative 1, right? So I have negative 1 in here, and then minus root 9 minus x squared. Dx? Plus, yes. I don't know why I did that. That good? Can we integrate that? I hope so. We spent several weeks on. Antiderivative of 1, of negative 1, is negative x. So the area equals 2 times, let's see, negative x plus, how about this? What's that? Close. If it was 1 over that, it would be. Do we have a formula for something that looks like a squared minus x squared? A formula. It's a trig sub for sure, but is it on our formula sheet? It's formula number, no, it's not 21. No. It's actually formula 30, which is not on your sheets. But do we all understand we could do a trig sub on this? Yes? I'm not going to go through the work. I'm just going to tell you what it is, okay? But I'm using, no, because 21 has plus. Yeah, but 30, which isn't on your sheets, does account for this. So according to formula 30, it's going to be x over 2 square root of 9 minus x squared plus 9 halves arc sine of x over 3, and that's it. And we evaluate that from 0 to root 8. That's it, whatever that is the volume, or is the area of that front face. Yes or no? I don't feel like plugging that in. You just get your calculator out. Root 8 over 2, root 8 squared is 8. Oh, that's nice, right? 9 minus 1, that's going to be 1. Root 8 over 3 arc sine. Ooh, I don't know what that is, but you're going to have to get your calculator out. You're going to get a nice decimal answer here. And that will be the area, right? The volume of the water will be that area times what? The depth, which was, or the height, which was 12. Okay? Can we turn the projector on, Vanessa? Do you mind doing that? Whoa. Seats way down there. Is it coming on? There it is. I'm going to have the computer integrate it for us. So 2 times the lower limit was 0. Square root of 8 is up top. The expression we were integrating was -1 plus the square root of 9 minus x squared. And let me put 2.0. I forgot my parentheses. That didn't take long. Okay, so 8.25, and let's multiply that times 12. 99.0025 cubic feet should be the result. Do you understand? What's the volume of the container? What's the volume of the actual gas tank?
It's 339.
Was it? So the volume of the tank, I'm going to say V of t for the tank, would be pi times the radius squared times 12, which it is what?
339.29.
339.29. That's the volume of the tank itself. What percentage of the tank is full? So take this number and divide it by that number. What would you get? Anyone got it? 29%. About 29%, approximately 29% full. So if I had restated the problem and I had said it was 3 feet deep, right, instead of 2 feet deep, you wouldn't do any calculus at all, would you? Right? I mean, that would be obviously halfway. It would be halfway. But because of the curvature of the tank, 2 feet up does not mean that it's, how tall is the tank? 12 feet? Sorry, 6 feet, right? 6 feet. And if we're 2 feet, if we're 2 foot high, right, 2 feet, we are a third of the way up, right, the tank? Are we a third of the way full? Not quite. A third would be what percentage? 33.333. So anyways, okay. That problem was in the book. I'd never seen that problem, and today I just happened to see it. I was like, oh, that looks fun. So I just thought I'd start class with that. That's kind of an interesting problem, though, right? I mean, you can actually apply this to something.
So did you divide the actual tank with the percentage that we got? And then that's how we got the
29. It should have come out to be 0.29, I guess, if you took the 99.0025 and divide it by the 3, whatever you got.
All right.
Yeah. All right, 7.2 today. I don't think there are. I think this is where in the class the notes are going to kind of just be what I do in here. Now I do have some older notes that I wrote that were taken in class that I might be able to give you, but they're not that organized. Yeah. So that means pay attention today and write down things, and I'll really stress if there's something really important that you need to have written down, I'll box it, put stars, and do a cartwheel, all right? All right, so what we're going to talk about now are volumes. That's the title of the section. And this is commonly referred to in Calculus 2 as what we call volumes of solids of revolution. And when we see the word revolution, we're talking about rotation, revolving, not like revolution, like here comes the new revolution, all right? This is just geometrically, we are going to create some solids by revolving things and try and find the volumes, right? That's what we're going to do. So before I can begin, we need to clear some things up. We just established a second ago that if I give you a cylinder, and I turned it on its side, okay, is that all right? Then if I call this distance here h, and then you know this part here is r, then the volume of that was pi r squared h, yes? Doesn't matter that it's sideways now. What if I take a cylinder, and then I take a smaller cylinder, there's the center, and I cut that cylinder out. So let's say that the outer cylinder, the bigger cylinder, has a radius of capital R, and the smaller cylinder has a radius of little r. Then what would the volume of this be? What's that? Volume of big one minus the volume of the little one, right? So the volume of the black one without a hole minus the volume of the red one, which would take out the red one from the big one. Yes? That's simple enough? So it should be, what's the volume of the big one? Pi r, capital R squared, right? Times the height. I didn't label height. That's the volume of the big one, minus pi small r squared height, yes? And they both have pi in them, don't they? So I'm going to pull a pi out. They also both have an h, but I'm not pulling it out the front. I'm going to pull it out the back, and you'll see why, and you just have to be patient with me here. So I'm pulling a pi h out, but I'm going to put the h in the back and the pi in the front. And then I'm going to put capital R squared here and minus r squared there. Do you agree that this is the same expression as this? Okay? No problems with that? This right here is what we refer to as a disk. And I know it doesn't look like a disk, but if you imagine a very, very thin cylinder like that, where your h is very small, then we create this thing that looks like a disk, right? You throw it, it's a disk. As opposed to this, which would look like very thin, you've cut something out of it, like, I'm going to exaggerate that cutout like this. We call this a washer. So a lot of times you'll hear instructors talk about this is the method of discs or the method of washers. What I'm about to do, okay? But the idea comes from these two pictures. If you have a solid cylinder with nothing taken out of the middle, it's going to form a disc. If you take a disc and cut out a center from it, which is another cylinder, you create a washer, right? Do y'all see the washer and disc? No questions? All right, let's proceed then. Let's figure out how we're going to find these volumes of solids of revolution. So let's take a very basic function, or let's say two functions. Let's look at the region bounded by the region bounded by y equals, we're going to go really basic here, x, y equals 2 minus x, and x equals 0. Let's take a look at that region bounded by those curves. So I'm going to draw it. Oh, by the way, the video for the solutions for the homework for 7.1 were posted this morning. All right, just so you know. I've started 7.2, but I haven't finished it. Okay. So this is why I brought markers today, because, and I know you don't have markers, and that's not really fair, but since I'm illustrating this, I think the markers will help you. So what I'm going to do is I'm going to start drawing these things, and I'm going to use colors. All right, so let's first start with this graph, y equals x, which is a diagonal like this. Everyone agree? Yeah? Then we have y equals 2 minus x, which is another line. How do I draw it? Okay, so it's negative x, which is this, but shifted up 2. So I have a y-intercept of 2. And then it goes down 1 over 1. So down 1 over 1, it should hit this one. Like that, yes? And then label it y equals 2 minus x. Finally, x equals 0, which is what? The y-axis. So x is 0 is the y-axis. So let's take a look at the region bounded by those three curves. Everyone see it? The region that's bounded by those three? All right, it's this region in here, isn't it? I could ask you right now to give me the area of that, couldn't I? If I asked you to give me the area, you would do vertical rectangles or horizontal? Vertical, right? You'd do vertical because you would have a function on top and a function on bottom. Yeah? But that's not what today is about. What we're going to do now is I'm going to add something to this. We're looking at the region bounded by these. Now, rotate that region about the x-axis. Find the volume of the solid formed. So you actually have to visualize this three-dimensionally. I mean, there's no way I can come over here and just pull this and rotate it and say, there, look at it. You actually have to see this. So can everyone imagine that I have this sitting, the whole thing is sitting out here? The x-axis, right? The x-axis is here. Come bring the whole thing out. We've got this little triangle thing right there, right? And we're going to take that triangle and we're going to rotate it around the x-axis until it comes all the way back up. And when I do that, as I rotate, it kind of leaves a trail behind it of triangles, and you get a solid, don't you? And what we want to know is the volume of that solid. Understand? Now I'll try and give you a better picture. Real quick, can we kill the lights? Just real quick. This isn't the same, come on. This isn't the same region that we're looking at right now, but see this right here, this purplish looking thing? Imagine that that's our triangle, right? And we take it and we look at that now, we look at that region, that purple region in three-dimensional space instead of two-dimensional space. Everyone see that? And then take that region and we start wrapping it around the x-axis. When we wrap it around the x-axis, we form this solid. And I can take a bunch of this crap out of here so you can really see it. So there's the solid that I would have had here, right? And what we are interested in is what the volume of that solid is. Later on, we'll also ask what's the surface area. But for now, this is where we start with the volume. Understand? OK. So the way we'll do it, the way we're actually going to construct it and determine the volume is to understand again what the integral meant, right? The integral symbol was a way for us to add up an infinite number of things, right? And what we've been doing is adding up an infinite number of rectangles, the areas, to get a total area, right? Now what we need to do is add up, oops, sorry, let me silence this. We need to add up an infinite number of volumes in order to get a total volume. Same process, just it's going to be a different sort of formula. All right, so let me show you the procedure for this. My drawing's pretty damn good. I'm happy with that. Here's what we'll do. I'm just going to kind of give myself a little space here to the right. So I'm going to erase these. Just kind of erase this a little bit. Since this is our first example, your picture may not be perfect the first time. It's going to take a little while to get used to how to set these up and giving yourself enough room to do all the work. Just bear with me, okay? Just for now. This is y equals that. All right, so here's how I do it. Here's how I recommend you do it. To the right of this, we're going to draw another copy of the x-axis because that's what we're rotating it around, right? And I'm going to draw, this is a curved arrow, a double curved arrow, which represents rotation, right? So this just helps remind me that this is the axis I'm rotating over. Then I'm going to come in here and I'm going to draw an arbitrary rectangle that's vertical in here. So I can do it anywhere, right? I don't recommend you draw it at the edges. Just put it somewhere in the center like we did before. There's my rectangle. Now we know that that rectangle is going to get infinitely thin, and we're going to have an infinite number of them, right? But that's just kind of a general picture. Bring that over, slide it over here to this, keep it off the ground just like it is here. Draw your rectangle just like that. Then come in here and do just kind of a quick label of what the top edge of that rectangle is going to be and what the bottom edge of the rectangle is going to be. So the top edge of that rectangle is always dictated by what function? This top edge, as I move this around, what function determines how high it is? The 2 minus x, right? So up here, the height of this rectangle will always be 2 minus x. Agreed? The bottom edge of this rectangle will always be determined by the red line, which is y equals x. Yes? Now, if I take this sliver, this rectangular sliver, and I wrap it around the x-axis, what would I get? Just that sliver wrapped around the x-axis. What would it create? A washer, wouldn't it? Wouldn't that create a washer if I wrapped it around the x-axis? Do you see it? Because you'll have a hole in the middle, wouldn't you? Imagine I have to take this and I have to wrap it around here. As I come around, I'm going to leave a space in the center, right? So it's going to look, when I wrap it, I'm going to draw the picture of it wrapped below. It's going to look like this. And it will have something cut out of the middle, wouldn't it? So this is a picture of the region. This is a picture of just the rectangle with all the other crap pulled out of it, right? Just the rectangle with what dictates the top and bottom of it. And this is what we call one slice. Okay, one slice of that. Do you know the volume of this slice? You just told me we just had a formula for it, didn't we? The formula that we had, I told you to write it in a certain way, and I said it would look weird, but just bear with me. We said the volume of that slice would be pi. It would be the capital R squared minus the little r squared, and then I told you to leave the h on the outside, didn't I? Okay, so for us, let's start out with what h is. H is this width, isn't it? Well, the height is the width. It's kind of weird, but that's what we're talking about when we say h. For us, what's h? Dx. It's the width of the rectangle, which we know that was represented by dx in our integral, wasn't it? So the width is dx. I'm not going to draw it here. I'm just going to come over here. This width becomes dx. Pi is not going to change. So what we need to do is determine the capital R. Capital R is the distance, right, from the center of rotation to the outer edge, right, of the washer, which if you bring this picture up here, remember our rectangle is actually, if I try and draw the rectangle in here, rectangle is actually in there like this, isn't it? That was that thing that got wrapped around. I don't know if that you can see that, but it's in there. And so we know that the distance from the x-axis to the top of this rectangle is the same as the distance from here to here, which is 2 minus x, isn't it? So the distance from here to here is 2 minus x. And I'm going, from here on out, I'm going to label this as the out. And what I mean by out is that this is the outer radius. If I'm standing here, that's the outer radius. Understand? So like if you're standing there on this axis of rotation and you see this disk around you, this washer, the furthest point out, the outer radius, is that distance from here to here. Yes? Then this distance, right, the little r will be from here to here, won't it? And what's that distance? It's x. It's the red part, x. And from here on out, I'm going to call that in, all right? Out for outer, in for inner. If you want to write outer and inner, you can. So back over here, this formula is going to be the out squared minus the in squared. Do you understand how that's working over here now? Capital R is the outer radius, square it. Little r is the inner. Do y'all see the geometry behind this? I mean, do you see the picture where the formula is all coming from? This is what I was trying to explain to you when we were doing Riemann sums, is that it's important to understand in that integral, the first integral we ever learned, right, that the f of x dx was height of rectangle, width of rectangle. Now, our new integral, every little piece means something in this new integral. The pi comes from the fact that it's the volume of a cylinder. The outer radius comes from the fact that it's a washer, subtracting the inner radius, right? And then this is actually the height of the cylinder formula. Okay, so let's plug this in. This would be pi. The volume of that little slice right here, this slice, will be, what is the out? 2 minus x squared minus the inner, which is x squared dx. That is the volume of this little slice, isn't it? So what do I want to do now? Add them all up. Add them all up. I'd like to take every rectangle that's in here, take infinitely many of them, and create an infinite number of slices and find the volume of all those slices and add them up. And that's what the integral allows me to do. So I'm going to now write down the integral. So keep in mind, this is the volume of one slice. One slice. Okay, the volume of the entire thing, okay, the volume of that entire solid wrapped around will be the integral from where to where? So 0 and then to wherever this is. We never checked, we never figured it out, but it is 1. You would set them equal to each other, or just do a quick visual inspection, right? If I plug 1 in here, I get 1. If I plug 1 in here, I get 1. So they do hit each other at 1. So 0 to 1. And then this, right? Pi can come out of the integral, can it? Then it's the 2 minus x squared minus the x squared dx. There we go. So long as we can integrate that, we've got the volume, which I think this would be a pretty simple integration. I guess since this is my first one, I'll take this one all the way. On the homework, when I'm doing the homework, I think I just set it up. I don't even go the rest of the way. Like on the videos I've done, I just do that and I go, and you can do the rest. All right, so this right here, I would expand this out so I get 4 minus 4x plus x squared. And then I'm going to subtract from that x squared dx. Collect like term. Oh, those cancel, don't they? So it's just 4 minus 4x? That's all I've got to integrate? Why are you so quiet? You don't seem too enthused about this at all. Antiderivative? What's the antiderivative of that? 4x minus 2x squared. Evaluating from 0 to 1. Yeah? Plug in. This is going to be pretty easy to plug in. If we plug in 1, what do we get? 2, right? Plug in 0, we get 0. So it should be pi times 2. So 2 pi. Holy crap. Okay. The volume of the solid would be 2 pi. And then whatever units you're in, you know, feet, meter, it would be cubic feet, cubic meters, whatever the unit is. You don't seem to like this. What's up? Thought y'all would really enjoy this. Okay, I'll try a little harder to impress you, all right? You know where I'm going.
What?
Classic problem.
Plastic Robert?
Oh, I thought you said classic problem. Okay. How about a classic problem? Most instructors don't show their students this, but I'll show it to you because I think it's worth it. All right, so how about this? Because you're worth it? Is that what you said?
Oh, yeah. I was just thinking,
Sphere. What's the volume of a sphere? 4/3 pi r cubed. Says who? Says the formula sheet, right? Says the formula sheet. And where did that come from?
integrating from the area.
Magic. It was magic. How could you come up with an integral that could give you the volume of a sphere? Take the area of what and rotate it around what?
Semicircle.
Semicircle. So what if we take half a circle and rotate it around the x-axis? Wouldn't we get the sphere? Better yet, instead of a semicircle, why don't we just take the first quadrant of a circle and rotate around the x-axis? And then times, actually it would be times 4, right? So look, I'm saying take a full circle, right? This whole circle goes around. Just take the first quadrant of a circle and rotate that around the x-axis, and what would you get? You would get this, wouldn't you? You get half of a circle, and then you just take that answer and multiply it times 2. Did I say 4? I said 4, 2. I'm sorry. Yes, so, yes, rotate that,
This is more sphere.
multiply it times 2. Yeah? Do you think we could do that? Sure. Well, you can do it too, but I'll help you. All right, so if we're going to do this, we need to figure out what the equation of that is, right? Because the region we want to rotate is just that, right? That's what we want to rotate. The rectangle we want to rotate looks like this. And we're going to do a vertical rectangle and just wrap it, right? And then add them all up. Then at the end of that all, multiply by 2 to get the other side. So can we get the equation of this function of x, this red thing? So where's that going to come from? The equation of a circle. Now this circle is centered at the origin, right? So I can use the x squared plus y squared equals r squared. And I'm going to use little r. That way, when we're done, it'll match up with the little r that's here. I'm not telling you what the radius is, am I? Okay. So can you solve this for y? Y squared is r squared minus x squared. Y equals square root of r squared minus x squared. And it's supposed to be plus or minus, right? Is it going to be the plus or the minus on this one? The plus, because it's the value of y, isn't it? And that value of y has to be positive if you're going to be up here. If y was negative, you'd be down here. You'd be on the bottom edge of the circle. So I'm going to take the positive one. Everyone good? That's the function of x up here. R is a constant in this problem, right? R is fixed. All right. X is a variable. R is fixed. So now what I'll do, that I've got that function written down, this is y equals square root of r squared minus x squared, is I will come to the side. I will label my axis of rotation. I will draw my rectangle as it appears to me. And notice that the rectangle always touches the x-axis, doesn't it? Right? That's why it's written that way. What is going to determine the top edge of my rectangle? What determines that? This red curve, right? That red curve is what determines that height. What about the bottom edge? Y equals 0, right? It's never changing, this bottom edge. I better do it in a different color. This bottom edge right here is this bottom edge, and that never changes throughout the entire problem, because as I move this rectangle left and right, that edge stays the same. All right, I know I'm going to rotate this. When I rotate, am I going to get a washer? Am I going to get a disc? Disc, right? There's going to be no hole in it. So I rotate. I'll do it below. Oh, terrible. Like this, right? Get a disc. And so when I have my disc and my axis of rotation here, I just need to get an outer radius and an inner radius. I want you to keep thinking of it that way. The outer and the inner. The outer is the distance from the axis of rotation to this top edge, which is the same as the distance from here to that red. What is that distance? It's actually just the function itself, right? Which is square root of r squared minus x squared. This is the outer one, right? What about the inner edge? It's 0, right? It's always touching. I'm standing at the bottom edge of this rectangle all the time. So the distance from me to it is 0. So this is 0. The 0 is the inner. Yeah? That's all you need to do the integration, to set up the integral. Now, we do need the limits of integration, though. Where are we going to integrate from? 0 to that point, r. It's the radius of the circle, isn't it? So we have it. It's the volume of this. We'll double the answer at the end. The volume of that is what? Integral, before the integral. Pi, okay, pi. And then integral, where to where? 0 to r, right? And then the outer one squared minus the inner one squared. D what for us? Dx, because I oriented my rectangle vertically. The outer was a square root. Sweet. Because when I square it, it's going to go away. I'm very happy about that. You should be too. And then the inner one, which is 0. That's really nice, isn't it? So the volume is pi times the integral from 0 to r of what? R squared minus x squared. That's it, right? Where, yeah, because that 0 is gone. What is the antiderivative of r squared? Be careful. Oh, careful. R squared x. R squared is a constant. May as well be the number 10. The antiderivative of 10 would be 10x, right? So the antiderivative of r squared is just going to be r squared x. So here's where we are. Pi, antiderivative r squared x, yeah? Now, the antiderivative of negative x squared, yes, that's going to be 1/3 x cubed. So minus 1/3 x cubed. And we're evaluating this from where to where? 0 to r. So let's plug r in. If we plug in r, what do we get? Let's see, pi, and then what? We're plugging in r for what in here? For x. So what's r squared times r? R cubed minus 1/3 r cubed. That's what I get when I plug in r, right? And then I plug in, so I say minus, now plug in 0. It's gone. What's 1 r cubed take away 1/3 r cubed? 2/3 r cubed. So we're getting pi times 2/3 r cubed. Right? Which is the same as 2/3 pi r cubed. And that's our answer. But that's half of it. So you double that answer, and you get 4/3 pi r cubed. If that doesn't get you excited, then nothing is going to get you excited in this class. All right? I mean, we just derived the formula for the volume of a sphere.
Can we derive the formula of a test factor?
Of what?
Like if we tried to take a sphere in three-dimensional space and rotate that around, would that not be possible?
Well, well, in 3D, take a ball and rotate it around, you'd make like a torus. You'd make like a solid torus. That would be, you could find the volume of that, but that would be a little different than what we're doing here. All right, so hold on. I want to finish this up. This right here is the volume of this, right? Is 2/3 pi r cubed. And so when you bring the other side of it in, you double this answer. 2 times 2/3 pi r cubed is 4/3 pi r cubed. There you go. All right, so it's kind of useful. These solids, I mean, you can kind of come up with some useful stuff. If you should ever need the volume of the sphere. See, this is the way mathematics works, though. You know, you use the math as a tool so that you can get yourself to something that people don't have to go through this over and over, right? Like, now you have a general formula for any sphere. You have the volume. Never have to go do that integration again. Okay. How about this one? Let's take, this is another example. We're going to take y equals natural log of x. We're going to take y equals 1, y equals 2, and x equals 0. We're going to take that region. Okay, so this is my region. And I'm going to rotate it about the y-axis. So in all these problems that you're going to do for homework, they're going to give you equations that create the region. They're going to tell you what axis, and when they tell you what axis, it'll say about something. And that about something tells you where you're rotating. All right, so the picture is important. Notice I haven't used a calculator at all. Y equals the natural log of x. So what do we know about natural log of x? Does it have an x-intercept? Where's the x-intercept of natural log? At 1? So how about here? At 1, I know natural log, and let me color code this. Just because it's fun, right? Get to use colors. I get to use colors, you don't. Unless you brought your colored markers, right, Christy? Okay, so natural log, we say dives down like this, and grows like this. I'm not saying you need to go buy colored pencils, okay? If you can do all this with your own, with the, standard lead. You don't have to have the colors. What else do you want to graph here? Y equals 1, where's y equals 1? It's horizontal line. Y equals 1 is a horizontal line. And it goes through y equals 1. So it looks like this. Y equals 2 is another horizontal line above that one, right? And x equals 0 is the y-axis, right? I'm out of colors. That's unless there's a different color in this room. I don't. Oh no. Oh, I have my blue gasoline color. What? Gasoline, not Vaseline. Our problem over there. Some of your classmates were being critical of the blue gasoline. All right, so there we go. Everyone see the region? Everyone see the region? That's our region, right? What is the axis of rotation? The y-axis, not the x-axis. So let me ask you, if we rotated this around the x-axis, we would get a solid, wouldn't we? Can you kind of visualize what it would look like? If this region came around the x-axis. Like a coliseum? Yeah, that kind of laying sideways, right? Like, right? I guess so. It would be like this, but then this would taper in. The inside would go in quite a bit. You would have, if you're looking through it, here's the outside edge. So this comes around, that really doesn't taper properly, but I would be able to put my arm through it, wouldn't I? Because it would have this hole as it came around. And it's kind of more like cut out here, right? Because of this curve right here, it'd be cut out and it would taper to a point here at the edge. These things aren't super easy to visualize, but you do your best. Now, that has a volume, right? That's not the same as the solid I get when I rotate this region around the wall.